Hey everyone! So here's a circuit that I think every EE hardware person should know. Especially if you're going to go into embedded systems or if you're going to design your own circuit systems, you're going to see this a lot. And chances are, you might even see this in an interview. So in this video, I want to share with you this circuit. So here's the golden question. What is a simple circuit diagram for a switching regulator? Let's say I have 12 volts and I want to bring it down to 3 volts. What would that circuit look like? So I'll draw it here on the board. This circuit is also known as a buck converter or a step-down converter. And what it does is it takes input voltage, V in, and it brings it down to a lower voltage, V out, across a load. And in this circuit we have a variety of different components. We have your load, you have a capacitor, inductor, a diode that functions as a switch, but we also have another switch up here. And this switch in real life will be implemented with a transistor, most likely. And the way it works is this switch will be turning on, off at a particular duty cycle. And you will find later on that the output voltage will be a function of the input voltage here, as well as the duty cycle with which you are turning on and off this switch here. So as I mentioned, this circuit's called a buck converter. And it's also known as a step-down converter. Now with regards to this switch, I will draw out the signal as a function of time that shows the on and off switching of this component here, this switch. X-axis will be time. So this signal will represent this switch. And when the switch is at 1, it means that the switch is closed or on. And when the signal is low at 0, the switch will be open or off. Now the time at which the switch is closed, where the signal is at 1, I will denote that time period T on. And the time during which the switch is off, I'm going to denote as T off. Now T on plus T off will add up to the total period of your switching cycle. And depending on the parameters you want with your circuit, might change efficiency as well as other factors, you might adjust the total period here. But we won't go into that in this video. So for now, just focus on this T on, T off ratio. So given our T on and T off, as well as your input voltage, the output voltage will equal the following. So V out, the voltage at your load, will be equal to your voltage input multiplied by T on divided by T on plus T off. This ratio here is also known as the duty cycle of your signal for your switch. So this is how you determine your output voltage, and you can set it accordingly. Now how does this circuit really work? Let's give a general overview on how this circuit works, and then we can go into some of the math to make things more clear and perhaps derive why this equation is correct. So let's give a general overview on how this buck converter works. Let's say the switch is on. Okay, so this is during T on. This switch will be closed. So what happens when the switch is closed? This means that the source will be supplying current through this inductor and the rest of the circuit. And because there's a diode here, there's a switch, that will be open. And so this is the loop that we're focused on. Now the current going through this inductor will attempt to increase. But due to the nature of inductors, there will be a voltage induced across this inductor in response to the increase in current through the inductor. Now what happens when the switch is open? When the switch is open, the source is no longer part of the circuit. And the inertia of the current that is already running through this inductor will actually drive the rest of this circuit. And because you have a diode here, this switch will now turn on to close the loop. And because the inductor now functions as a current source, that current will slowly decrease when the switch is open during your T off period. And after this T off period, the switch will turn on again and close, and you will again repeat the cycle where the voltage of the input is now part of the rest of the circuit, and this diode here is open. And so T on, T off, T on, T off. Now because your switch is turning on and off, and you're switching between these two states, you will have a V out that is basically oscillating with a sort of spiking pattern, which is why you need this capacitor here to smooth out that voltage. And here's one more thing to keep in mind. When this switch is turned on, the current being pulled out of the source is usually higher than its rating. However, the source is not damaged usually because T on is short enough where no damage occurs to V in. And when T off happens and the switch is open, that will give time for all the components to cool down. And so this switching mechanism is key, otherwise this circuit would just not work. So now that I've explained qualitatively what this circuit does, let's go into the math to understand where this equation came from. So let's look at the first case where the switch is closed. This will be our T on. When the switch is closed during T on, the current will be drawn from V in through the rest of the circuit. Most notably, there will be an increase in current through this inductor. However, due to the nature of inductors, there will be a voltage created across the inductor in response to the increase in current. I will denote the voltage across the inductor as VL, but because we now have a voltage induced across this inductor, that will ensure that our V out is smaller than our V in. You already know from physics class that the inductor basically stores a magnetic field when you're trying to drive current through it. And it's always trying its best to resist any change in current going through the component. If you're trying to increase current through an inductor, the inductor will try and fight that. If the current through the inductor is decreasing, the inductor will also try and fight that. That's the nature of the inductor. So now that I have this switch closed, what would my equation look like if I'm trying to analyze this circuit? Well, we can do simple KVL. That's Kirchhoff's voltage law. So we know VL, V out, and V in. So we have a simple equation here. Let me draw some signs just to make it clear. So we have V in equal to the voltage across the inductor plus V out. So now that we have this equation, what do we know about VL? Well, we already know the equation for the voltage induced across an inductor, right? The voltage induced across an inductor would simply be the inductance multiplied by the change in current with respect to time. So let's write that out. Now when we look at this equation, we realize something. We see that we know that the switch is only closed during a very short time interval T on. So we can actually substitute that for our dt as well as the delta I, which represents the change in current running through this inductor here. So let's write that out. I will denote the change in current through the inductor as delta I1. So if we substitute this into this equation, we have the following. Now that we have this, we have the equation for what happens when the switch is closed. Now after this T-on interval, which is not very long, the switch will then open. So we're going to be in this T-off interval. So what happens when the switch is open? The source is no longer part of the circuit. And as I mentioned earlier, the inertia of the current running through this inductor already, the magnetic field stored inside this inductor, so to speak, this inductor will then function as a source itself. And this diode here will close the loop. And so we basically have a circuit comprised just of the inductor, the load, as well as the capacitor. Okay. So if we wanted to write out the equation for this circuit during the time interval T off, what would that look like? It'd be even easier than before, right? It would simply be VL plus V out equals to 0. Yeah, because looking at this loop, all we have is this voltage drop and this voltage drop. This diode here is short. So now that we have this equation, we can do the same as before, where we can write out the voltage drop across this inductor as a function of the inductance as well as the rate of change of the current running through this inductor. Now because this inductor is functioning now as a current source, and there is no V-in connected to it supplying the current, it's likely that the current running through this inductor will slowly decrease, even though the inductor itself will resist that change. But looking at this equation here, we will do the same thing we did here, where we can substitute for dt with the time interval t off. And we will substitute di for a delta I2. Okay? So we know that there's going to be a change in current during the off interval. And this is the equation we have right now. And we can take this equation and substitute it into our equation here derived from Kirchhoff's laws. So now we actually have a system of equations here. We have equation 1 and equation 2. And we can use these two to solve for the relationship between V out and V in. But what is the variable that we want to get rid of here? The variable that we kind of want to get rid of here is delta I1 and delta I2. We just don't know what those are. But we can actually figure out the relationship between delta I1 and delta I2. How do we do that? In order to figure out the relationship between delta I1 and delta I2, we need to understand that with this switching that is happening, eventually the circuit will reach an equilibrium state. A steady state, if you will. This will mean that after each switching cycle, the energy stored in each of the components, for instance the inductor as well as the capacitor, the amount of energy stored in each of these components will be constant after each on-off cycle. If the energy of each of these components is constant after each on-off cycle, that also means that for the inductor, the current running through the inductor will also be constant after each on-off cycle. This will mean that the total net delta of the current running through this inductor after each on-off cycle will be 0. Delta I1 plus delta I2 must equal 0. So we found the relationship between delta I1 and delta I2. Our equation is basically solved. We just need to get delta I1 in terms of the other variables, delta I2 in terms of the other variables, and then substitute them into this equation here. Okay, so we're almost done here, so let's just crank out the math and get the solution. I'm going to clean up the board just to make it easier to see. So I'm going to rewrite both equations here. And now, all we do is substitute it into this equation here. And voila, we have the solution. Notice the inductance canceled out here. But we have V out is equal to V in times the duty cycle, T on over T on plus T off. Okay? So we have just solved for the output voltage as a function of the input voltage and the duty cycle. So there you have it. This is the derivation for the equation of a buck converter, which is a type of switching regulator. In addition to switching regulators, you'll also work with linear regulators likely, and there's usually trade-offs between the two. For instance, switching regulators might be more efficient, linear regulators might have less noise, and it's up to the engineer to determine which one they want to go with. But this buck converter here is a circuit that you will likely encounter in your lives if you work on hardware. Anyway, I hope this was interesting and that you had fun. Happy New Year, everyone, and have a nice day.